This week, your bank's random numbers may be less random than you think, which matters because encryption treats those numbers like locked doors. The catch is simple. Computers do not roll dice, they follow recipes, and a recipe can repeat itself if someone learns the starting point. That is pseudo-randomness, useful fake chance from a fixed recipe, and for daily life, that fake chance usually works beautifully. But real machines have tiny leans even when physics supplies the noise. A bias is just a lean in the output, so a pattern can hide where your screen still looks safe. In games, that lean barely matters. In cryptography, it can matter. An attacker may need only the leak, not the whole secret, because weak starts have broken real keys before. A future quantum attacker makes that old weakness feel less theoretical. So the question becomes whether flawed chance can be repaired at all. At ETH Zurich, the team stopped asking the generator to be perfect and asked if weak chance could be forced to prove itself. Classical computers cannot give that guarantee by themselves, so they used 2 quantum chips joined by a 30-meter frozen tube, where each chip held a qubit, the smallest quantum decision point. The hardware sat near absolute zero, where tiny disturbances stay manageable. Then microwave photons carried the link between the separated chips. That link creates entanglement. The chips behave like one shared system, so the weak generator only chooses which question each side gets, and the chip answers with a clean 0 or 1. The separation matters because ordinary messages cannot cross in time, so a hidden classical script has less room to explain the match. But the lab record is still raw, messy, and not yet a key, which is why the proof has to come before the extraction. The proof is called a Bell test, and it asks whether separated answers agree too strongly for a shared recipe, so if the test passes, the hidden pattern story loses. ETH setup mattered because it ran fast enough and clean enough, then an extractor algorithm kept only the certified unpredictability. The clever part is that you do not trust the box itself, you trust the public math around what the box produced. For you, that difference is not philosophical, because a guest session key can turn privacy into paperwork. Digital identities, lotteries, and blockchains all make the same bet. Future attacker does not need magic, only better pattern hunting, and post-quantum encryption still needs keys born from clean chance. That is the uncomfortable part. Randomness sits underneath everything else, so security can fail before the password ever appears. Renner and Wallraff's twist was not a better die, it was a way to catch any die that leaned. That changes what a trustworthy random source can mean. To be straight, this is lab-scale hardware, not tomorrow's phone part, but a standard source can serve many systems at once, the way atomic clocks quietly serve time to machines everywhere. Your bank would not need the freezer, only the certified stream. ETH's sheep image makes the difference visible because the safer output erases structure instead of merely hiding it. So the same idea returns to the first login screen, where a weak start can become safe after physics audits it. The trust moves from a private box to a public experiment, which is why quantum security is also a story about better chance. So your bank's next random number should come from nature, not a recipe.